In this video, I'd like to talk about the process of lipogenesis. And lipogenesis is the formation of fat or triacylglycerides. Now, if you recall, triacylglycerides are the storage form of fatty acids. So we want to convert these fatty acids, we want to store them as fat or as triacylglycerol. So triacylglycerol or triglycerides, both are fine. And we get them from combining two molecules. So let me write this down. Lipogenesis is the process where you're forming triacylglycerol from two components, from glycerol and three fatty acids. So let's actually draw them right here. The first one is known as glycerol. Glycerol has 3 carbons and hydroxyl groups on each carbon. And then all the other atoms bound to carbon are just hydrogens. So this is glycerol. Now we also have 3 fatty acids, as I already mentioned. And let's do them another color. Let's do them green. So you have this first fatty acid. Let's make it like this. And I want to point out something really important. That fatty acid has already been activated into fatty acyl-CoA. This is absolutely essential. You need to convert it into fatty acyl-CoA. So there's actually a CoA group here bound to it. And let's draw another fatty acid. And again, we have our coenzyme A, sulfur right over here. And then let's draw our last one at the bottom. And again, we have our coenzyme A. So if you recall, we had to convert the fatty acid into a fatty acyl-CoA using the enzyme fatty acyl-CoA synthetase. And we actually required 2 ATP to do that. So essentially we need this 2 ATP, we need this activation for each of the 3 fatty acids, which we're going to combine with glycerol to form our triacylglyceride. So we're going to combine them together. So plus, plus, plus. Now let's actually look at how this process happens. So the first thing that we're going to do is we're actually going to start with glycerol. So let me actually erase this. So the first of the 2 ingredients is glycerol, and we absolutely need glycerol to form the triacylglyceride, right? It's in the name. So how are we actually going to form it? So since we used pink or purple, we're going to keep that color. In order to form our glycerol, in order to form our triacylglyceride, we actually need to convert this glycerol into another molecule. And this other molecule is known as glycerol 3-phosphate. We need to use this precursor to make our fatty acid. So the question is, how can we get this glycerol 3-phosphate? Well, there are 2 ways we can actually get it. We can start with glycerol and convert it into glycerol 3-phosphate. And the enzyme that allows us to do that is known as glycerol kinase. And here we actually need some ATP. This process happens in the liver. So this one here happens in the liver. Now you can also make it from another molecule known as DHAP, dihydroxyacetone phosphate. So we can draw an arrow right here as well. And in this process right over here, to convert from DHAP into glycerol, we actually need the consumption of NADH. So we need to add some NADH for this to happen. So we need NADH, and that NADH is going to be converted into NAD+, as you guys already know. So this is actually a reduction step right over here. And this process takes place in the liver as well, or it can happen in the adipose tissue. So in either of these two tissues. And the enzyme responsible for this step is known as glycerol 3-phosphate dehydrogenase. So I can actually write that down here. Glycerol 3-phosphate dehydrogenase. And recall, we're adding an ATP here using the kinase, and the result is we're adding a phosphate onto the third carbon, the third position of the glycerol molecule. So either way, we have our glycerol 3-phosphate. This is going to be our precursor in order to start making our triacylglyceride. We're going to combine this now with free fatty acids. So let's do that right here. So let's look at the first step. So what happens first? Well, the first step is we're going to take that glycerol 3-phosphate that we made. This can happen in the liver or in the adipose tissue. So let me actually draw the structure of glycerol 3-phosphate. So here we have glycerol 3-phosphate. And what we're going to do is we're going to combine that with the first fatty acid. So if you recall, the first fatty acid looked like this. So we're going to combine it, right? We had our C double bond O, we had our CH2 14, CH3, and then we had our, it's actually this in a different color, coenzyme A. Okay, and what's going to happen in this step, we're actually going to lose this coenzyme A, and we're going to form an ester bond between this C double bond O and the alcohol portion of carbon number 1 of the glycerol molecule. So let's actually draw that here. Right? So now we form this first ester bond, and we added one fatty acid to this glycerol 3-phosphate. This molecule right here is known as, let me write this down in blue, lysophosphatidic acid. This is the molecule that's formed when the first free fatty acid is added to the glycerol molecule. So in the next step, we're actually going to add another fatty acid or another fatty acyl-CoA to this lysophosphatidic acid. So we're going to add another fatty acid. And the interesting thing is that the second one that's added is actually an unsaturated fatty acid. So the second one that we're going to add is going to look like this. It's going to have a C double bond O, and then we're going to have CH2, 11, C double bond C, CH2. So anyways, it has a double bond somewhere within that structure, right? So here, what's going to happen, and again, you have that coenzyme A, let's see that in green, and this coenzyme A is going to be lost in this step. So the end result, what you get, is going to look like this. Again, we're still going to have our phosphate group on that first carbon, so that's not really going to change. But on that carbon number 2, we're going to add our unsaturated. So we'll still have that first carbon that's bound to the first fatty acid. And now the second carbon is going to be bound to the unsaturated fatty acid. Right? And this R actually is an unsaturated. So the C double bond O is bound to a hydrocarbon chain, but that hydrocarbon chain has a double bond somewhere in there. Right? And now let's actually keep this molecule. Let's actually erase everything else. So now that we have attached that second fatty acid to the glycerol 3-phosphate, remember that second fatty acid is actually unsaturated. And the molecule that we form now is called phosphatidic acid. So this molecule here is known as phosphatidic acid. And this molecule is really interesting because it can be used, it can be utilized to make phospholipids by adding a head to it. It can be used to make phospholipids. But it can also be utilized to make triacylglycerides or triacylglycerides. So it can actually be used to make both. However, in the next step, what we actually have to do, we cannot stick another fatty acid because there's a phosphate in the way. So we're going to have to remove that phosphate via a hydrolysis reaction. So we're going to have actually a phosphatase, and the enzyme is called phosphatidic phosphatase, because this is a phosphatidic acid that we have to remove a phosphate from. And what you're going to get is a product that looks like this. So it's still going to have the two fatty acids attached, but now the phosphate will come off and there's just going to be an OH here. This is actually, you can think of it this way. There's this hydroxyl group, which is going to act like a nucleophile, right? And what it's going to do, it's going to attack here on this phosphate, causing the electrons to shift here. And in the process, they're going to kind of go back to reform that double bond, knocking this off. A little bit of organic chemistry, Don't worry if you don't really understand how it occurs, but essentially this phosphate will be plucked off by this phosphatase. And now we're ready to add our very last fatty acid. So we can now add our last fatty acid, which is actually a saturated fatty acid, very similar to the first one. And we're going to have a glycerol molecule bound to 3 fatty acids. Oops. So now we're going to have all of the fatty acids bound to the glycerol molecule. And if you recall, that second one is unsaturated. And the bonds that we form are ester bonds. So now you have 3 fatty acids bound to glycerol by an ester bond. And the molecule that we form here is known as triacylglyceride. And by the way, when we remove the phosphate from phosphatidic acid using the phosphatase, we form the diacylglyceride. So diacylglyceride. And we add the last fatty acid to the diacylglyceride to form our triacylglyceride, which is the storage form of fatty acid. That's how we store the fatty acids. And in the process, we're actually going to lose our very last coenzyme A. So we lose 3 coenzyme A per every fatty acid that's added to the glycerol molecule. Now let's do a quick recap. So we have our glycerol 3-phosphate that's going to combine with our first free fatty acid. And when it does that, it's going to give us a structure called lysophosphatidic acid. The enzyme that's responsible for bringing that first fatty acid is known as acyl transferase. Acyl transferase. And in the process, we lose a coenzyme A. Then we're going to add our second fatty acid. So we're going to add our second fatty acid to this lysophosphatidic acid. So we're going to add our second free fatty acid. And we're going to form phosphatidic acid. Phosphatidic acid has 2 fatty acids bound to glycerol 3-phosphate. And the enzyme needed to add this second fatty acid is not a surprise, it's still acyl transferase. Because we're adding that acyl group to the lysophosphatidic acid. And in this case, in this step, we're going to lose another coenzyme A. In the next step, we're going to convert that phosphatidic acid into diacylglyceride by actually removing a phosphate. So in this case, we're going to get rid of a phosphate group. And the enzyme responsible for this reaction is the phosphatase, specifically phosphatidic phosphatase. And in the very last step, we're going to add our very last fatty acid to the diacylglyceride to form our triacylglyceride. And the enzyme responsible for this is not really a surprise. It's again going to be our acyl transferase. And this enzyme in the last step is going to add our third fatty acid. So let me actually put that here. Plus third free fatty acid to form our triacylglyceride. This is the storage form of fatty acid. Storage form of our free fatty acids. Okay? It can also be known as fat. So this is an important storage molecule. It can be used later when we need to for energy by being mobilized back to free fatty acids, for example, in adipose tissues. It can also be converted into VLDL. So this triacylglyceride can be packaged into VLDL in the liver so that it can be stored as triacylglycerides in the adipose tissue, and it can be mobilized in adipose tissue by being converted back to free fatty acids when glucose levels are low, when we need to send that free fatty acids to other tissues like the muscle and the heart so that they can use those free fatty acids for energy. And remember, the second free fatty acid bound to the second carbon of the glycerol is actually going to be unsaturated, and that means it's going to have a double bond. Naturally, most of the time, the overwhelming majority is going to be a cis double bond, and that double bond gives a kink to the molecule, right? And that makes this triacylglyceride, it actually is going to reduce its melting point. So it's going to make it a liquid at room temperature. And it's very important that we have our triacylglycerides in liquid form, because we don't really want them to be a solid globule in our adipose tissue where they're stored. Instead, they are a liquid form, and they're soluble in the cytosol of the adipose cell, and that allows the lipases, as we already looked at in the last video on lipolysis, to actually access those ester bonds that we just formed and hydrolyze them to release the free fatty acids, which can then of course be sent to a variety of tissues, mobilized, it can be sent from the adipose to the liver, to the heart, to the muscle, or it can enter the mitochondrial matrix and enter beta oxidation to be burned to generate a lot of ATP. Remember, 129 ATP molecules per 16 carbon palmitic acid.